Hi everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials in Manufacturing Innovation, and we have a brand new paper to talk about, and this one comes from my own group here at the University of Utah, actually with contributions from Leng Tang and his advisor Leonard W. Tang. They were at the School of Material Science Engineering, Nanyang Technological University in Singapore. Now, I'm really excited about this. This paper has to do with a systematically verified experimental thermoelectric data set. Now, I've been passionate about thermoelectric data sets for a very long time. In fact, this work is based off of one of the early papers that I did in my career. This one right here was published in Chemistry of Materials. It was a data-driven review of thermoelectrics where we scraped a bunch of data and put together an early database here. And there's been a lot of people that have built on these over the years. For example, this one just published in 2022 is another example of a thermoelectric data set coming from experimental measurements. Now, as great as those databases are, they are small, and there's been a lot of work done since then. And so we want to grow that database, paying attention specifically to doped materials and high-performing thermoelectric materials. So that's what we set out to do here. We did the following. We took the existing databases, our materials research laboratory database published in Chemistry of Materials, and this experimentally synthesized thermoelectric material database, the ESTM, and we combined that with new data that we collected directly from the literature to create the largest thermoelectric database to date. Furthermore, we did something else. We underwent a process of systematically verifying and extracting transport properties, identifying them, removing duplicates, and standardizing the composition labels, which was a huge problem if you looked at the original databases. The result of this is something that we call SysTem, or Systematically Verified Thermoelectric Database. Let me tell you how we did it. We went about searching for new materials using Google Scholar. We searched for things like thermoelectric or high figure of merit. We found a ton of articles. Most of them had the data reported in graphs, not text, which means that we're going to be pulling data out of figures. The tool we used was WebPlot Digitizer. We were doing this in manual data collection mode. Something else we did is we standardized the units. Sometimes these get reported in all sorts of crazy units. We were able to focus on a common set. And specifically with the way that compositions get reported, it's kind of the Wild West. Some people do it in weight percent, some do it in atomic or stoichiometric ratios. Here we unified it. All right, the initial data sets, how big were they? Well, our original MRL data set had grown from the time of publishing it. It had grown to about 1,800 data points, and you can find it on GitHub. Meanwhile, the paper from Nanchang had about 5,000 entries from about 197 different works. And then we had to go about validating the data set. So apart from just deleting duplicates, which is important, we also started to look for errors, things like missing links or incorrect values, either zeros or extremely large values. And we started to look for errors that might also be associated with incorrect unit conversions or manual data entry. The workflow looks something like this. Start with manual correction, look for duplicates and remove those, look at systematic verification of values, and then provide a composition standardization. In the end, we ended up with an awesome data set. It is the biggest to date, over 8,000 data points, 8,458, covering 1,426 unique thermoelectric materials based off of this reduced formula. That's amazing. It spans 70 different elements in the periodic table from 358 works taken from the years 1991 to 2024. During our systematic verification step, I was surprised to learn that we actually removed 615 entries, a significant reduction to improve the quality of the data set, and that the number of mixed formula formats was relatively small, only about 2.5% of the data. Ultimately, this is what we extract. If you look in the database we extracted, we get composition, temperature, the thermoelectric properties, and the metadata. When you look at the thermoelectric properties, that can be broken down into these 7 key transport properties: ZT, electric conductivity, Seebeck power factor, thermal conductivity total, as well as lattice and electronic contributions. And you can see how many entries we have for each of those. Some of those have fewer, right? It's harder to measure thermal conductivity, so there are fewer entries. So you see the lattice and electronic have only 2,000 entries, whereas these others have typically nearly 8,000 or more. You see a distribution of where the articles came from, mostly in recent years. You see a heat map of what elements are used. Again, not surprising to people who work in thermoelectrics, where these elements are and what types of ones are being used. And then you see these really interesting histograms of the properties that we extracted in these high-performing materials. So you see these sort of, what are the ranges that are typical for these high-performing materials for all these different properties that you might care about. And ultimately, we can extract out the top-performing materials. So for example, the 5 top materials in terms of ZT that we extracted all came in the last 5 years, with ZTs ranging from about 2.5 up to just over 3. one last thing we tried to do was divide the database into doped and undoped groups. Now, this is tricky because there's not a universally accepted sort of distinction between doped and undoped or alloying. Sometimes it's described in the paper and sometimes it's not. What we ultimately decided to do was just look for thresholds. We said if a certain element is present below a dopant ratio threshold, we chose 10%. You could have chosen another. But that's what we used to label it as doped or not. Using that 10% threshold, we found that about 78% of the materials in our system database were doped. Not surprising. Also not surprising is if you look at the best materials, then they tended to be in the doped category as opposed to the undoped category. So if you are somebody interested in data-driven science and you care about thermoelectrics, this is the database for you. We've done a lot of work to make it available. We think it is the best in class, and we hope you'll check it out. You can find it at GitHub, and I hope that you'll read all about it in the latest issue of IMMI.